Hello, how are you doing? I hope you're doing good.
Yep.
Okay, so good. Let's take a look at the lab for today. We'll start in about a minute. So today we're going to do lab 6. And I had also posted an image for your code there. We'll go over the code. Okay, so we'll go ahead and get started. Let me close out some documents. So today we're going to do sequence in LC-3. The most popular sequence that you see in academic is your Fibonacci number. Fibonacci is pretty fun. It's a way that we can look at how we can implement different algorithms to be able to generate a numerical pattern. So at the beginning of the lab, you're going to see when you download the document, it talks about Fibonacci number. And so sequence is just a set of numbers that we look at with a certain pattern. So in this case, we see Fibonacci in a lot of things that we use, right? Like when you eat pineapple, that has a numerical pattern that represent Fibonacci. When you look at a shell, right, a seashell, you would see the numerical pattern that's represented in Fibonacci. So it is a very common sequence that we address in computer science because it's easy to understand and we can implement different types of algorithm with it. So at the beginning, it gives you a little bit of information about Fibonacci. Leonardo Pisa was the mathematician that came up with Fibonacci sequence. And also, according to history, that this sequence is actually was found earlier on in India. So for Fibonacci algorithm, we often look at how we can create functions to be able to generate the values. A lot of times you would see it's either used with a loop, which is an iterative process, or sometimes you would see recursive function being used with it. And so for the parallel and distributed system, you would see that it is implementing Fibonacci. You also see that in data structure and graphs and other areas that would be useful to understand how Fibonacci works. And so I put a little link on TED Talk, and it talks a little bit about the golden numbers and Fibonacci. But just to kind of have a better understanding on what Fibonacci is, sometimes you would see that Fibonacci start with the 0, and sometimes we would start it with the 1. Often that you would see that it starts with the 1. In the case that if it starts with the 0, you would have the first two value, the 0 and the 1, as your initial start. So that's going to be your seed. So if my n of 1 is 0 and my n of 2 is 1, then I would take that value to generate the next value. So I would take 0 plus 1, I get a 1. And if I started with a 1 and another 1, so this is my initial value to begin my sequence, I would take those two values add them together to get the next value, which is a 2. And I would continue to do that. So if I take a 1 plus a 2, I get a 3. A 2 plus a 3, I get a 5. So in order to get the next value, you would take the 2 prior numbers and add them together. And that's how you're going to be able to get the next value in the sequence. And it could be infinitely going. So here I talk about how we can generate the sequence by adding the 2 previous numbers. And so when you look at that function, when we say f of n is the next value, we would say f of n minus 1 plus f of n minus 2. And this is what you normally see the implementation for recursive function. We would take the output, which is the return value from the function, and we would add it, right, with the return value from the prior function. And that's how we're going to be able to get the next value. So in the seed value where it is 1 and 1, we would add them together. In some cases, we would have the seed value of 0 and 1. So it varies, but you're still going to have the same sequence throughout. So in our program for today, we are to create an LC-3 program that's going to compute Fibonacci number. And we want to make sure that we don't have an overflow. So we have to implement the overflow control here. And you would represent the n as the big N here. So your f of n is the largest in the sequence. So the requirement for our problem is that the integer n is in the memory location at hex 3100. That's where you're going to find the n value. Your f of n is going to be in the subsequent location, which is 3101. Your big N is going to be at 3102. And your f of big N is going to be at 3103. So in this case, if we're looking at f of 6, right, we are going to start with 6 because that's the n value, the small n, at 3100 for f of 6. So 6 is going to be at hex 3100. Now we want to find f of 6. So f of 6, when it computes it, it's going to be at 3103. Okay, so f of 6 is actually 8. And so for your n value and your f of n value can be found in the location like this. So at 3101, we would see 8. And then for the 3102, we would see n and f of n. So when you simulate your program, this is the location of the address where you would find your values. So in the pseudocode, what we want to do is we want to break down all our subtasks so it's easier for us to be able to write our program. So this problem can be solved with iteration, where that would be using a loop or loops, where in other cases you would see that it would use recursion. So part of the lab manual, this is what's given to you. So in this case, we would say if n is less than or equal to 2, then f is 1. Why is it this way? Why is there a condition like this? If you take a look at the function, right, we have to have the seed of 1 and 1 to start our sequence. So it's saying that if n is less than or equal to 2, it's going to be 1. Those are our seed values to start our sequence, which is here. Okay. Else, we would have A is going to be 1 and B is going to be 1. So f of n minus 2 and f of n minus 1 is 1 and 1. And in the case, if we're using iteration, we would implement a for loop. So as you loop through, you would be able to take the two prior value, add it together, and then insert it into the container. So you would have 1, 1, and then you would take 1 plus 1, you're going to get a 2. 1 plus 2 is you're going to get a 3. 2 plus 3, you're going to get a 5. 3 plus 5 is you're going to get an 8, and so on. So here are your seed values, and we talk about the for loop here. So the loop doesn't actually start until your n is 3, which is where your index is, right? And so we would start the loop where n is going to be 3, and we continue to generate the value by looping until we reach the max n value. So if I need to find Fibonacci number for n is 80, right, I would loop it until n is 80. And so based on our function, we know that we would get the result by adding a and b, which are our seeds, right, to get to the third, and then we would take the two prior from the current location and add them together. So this is our function. F of n is f of n minus 1 plus f of n minus 2. And as you move through the sequence, your B is going to become A, because now when you go from the first and the second position in the container, you are going to move it to the next one after you generate the third number. So the A is going to become the second, the second value is going to become the first, and the third value is going to become the second, which is what's stated here, right? So what you see is when we come back up here, right? This is the first two. As I compute and I found my third value, the A is going to be this one, the B is going to be this one, and the F is going to be this one. As I would take 1 plus 2, I'm going to get a 3. And as you proceed to the right and you continue to generate your Fibonacci, it's going to shift the A and the B value and the F value to the right as well. So you're going to increment 1 to the right. Okay, so you need to see that in order to understand this. So part of the criteria is to detect overflow. And so what we want is we want to implement a for loop, but we also need to make sure that we check for F is negative. Because in the case that it is, right, we have to place a 1 in the front because it is sign extended. You got to make sure that you represent the binary as equivalent to what is assigned. Now, when you exit the loop, F does not contain the value f of n. To obtain f of n, you have to modify the algorithm as shown below. So this is one part that we have to add into our code. And then this is another part that we have to implement to make sure that we control the flow. So we know that A and B starts with 1. This is your seed value at the beginning for the first two. And your loop index at this point, your I is going to be 2. So here is, we know that to generate the next value, which is F, we would take A plus B or B plus A, which is our function. Now, to check for overflow, we want to check for negative. So if F is less than 0, then your big N is going to be the index, and that's going to exit. Okay, because it states that here, where if it's negative, then we're going to have overflow. So we want to check for overflow. And in the case that it is less than 0, then we would indicate that your big N is going to be your index value. And then we're going to halt. And as we proceed in finding the F, we're going to shift, right? The B is going to become A and the F is going to become B. We just talked about this. So that means that when you're looking at the sequence, right, you are going to move one down to the next. So I'm moving to the right. So that means that I'm going to increment my index, right, from the third value to the fourth value, and so on. So that makes sense in that we would take the I plus 1, the index plus 1. Okay? So as you increment, as you generate more value in Fibonacci, you're going to do an I plus 1, which is what's shown here. So we need to implement both of these listings into our code, and this is what you're going to see throughout the program. So that's why I want to spend a little bit of time talking about this. Okay? Any question before we go into LC-3? And if you're looking at the assignment, I added the image for the code, so you can, it's not too long, so you can go through and you can do it like this so I can explain it to you. But like I said, right, everybody solved the problem differently. This is one way to solve the problem. If you want to come up with another way to solve the problem, see if you can, and then you can write your own program based on what you've learned. So when I pseudocoded out, right, this is the steps that I went through. And so I just want to run through this so you can see. And this allows me to set up some form of procedure so I can break it down into the subtasks. And I just simply use like a number alignment to do this. So I have to have some kind of function called Fibonacci or some function. And I know that n is the index of the position of my number in the sequence, right? Just like how you solve for the sequence, your n is the location where that number in the sequence is. And in the problem, it tells me to fill the n at hex 3100. So that means that I have to put that into my data section to initialize that memory address for n. And I know that I can start with n is 1. That is the first number of my sequence, 1. So that means that I need to add 1 to the register because that's my seed value. Then for n is 2, the second number, I also need that as a seed value. So I need to add that to the register. My sequence begins when n is greater or equal to 2, or so I need to go after my seed to be able to implement the loop. So with that, we would branch the positive after comparing 2, which is where we subtract 2. Anytime that you see comparison like this, you know you have to operate the subtraction. This allows me to set up my loop. For my function, this is what you see with Fibonacci function. F of n is f of n minus 1 plus f of n minus 2. I know that I need to fill f small n at 3102. I would then need to implement a for loop. And the way that I would count for my for loop is my counter is going to be n. And my index is going to be I. And for the subsequent loop, it's I plus 1. So that means that I set register for I, and then I can increment it with 1 when it loops to the next round. So based on the listing, we also know that F is going to be A plus B. So at one point, A is going to be equal to B. as it generates the F value. So at the beginning, I need to seed A and B at 1. And so that means that I add 1 to the register. And to reassign for this part, I need to copy the register of A to B, right? So as you add it for A, if I wanted to make it for B, I can just copy the register. And for F, I know that it's A plus B. This is part of the listing that's given to us in the problem. I would need to operate the addition for the register that holds A and B. One of the criteria we know that, or based on the function, we know that F could also be B as we generate the value in Fibonacci. So when you see this, it is a reassignment. So we are going to copy the register of B to the register of F. Then we're going to store the value to the labels as we fill them. And so with that, we can have a rough idea of what we need to do with our Fibonacci program in LC-3. Okay. Any question?
How do we stop the loop? Like how do we know when to stop it? Because you could keep adding, right?
Whatever the value that you set for n, so when you run the program, you have to set the n value.
Oh, okay,
right?
okay.
Yeah, so it's gonna stop when it reached the maximum because it's a for loop, right? It starts at the 3rd position and it's gonna go. So if I set it at 70, then it's gonna go until the 70th position and it's gonna exit after.
Okay, thank you.
So you're welcome. So your input is your n value. That's what I'm saying. All right, so let's take a look at the code. And I had this written out in Microsoft Word, but you can see the image on the assignment page so you can follow along and type. So we start with origination address at hex 3000 always. I'm going to load the label small n, the lowercase n, to register 1 because this is where we can use the set value. That's our input. Then I clear register 2. So I initialize register 2 at 0. That's a clear, right? And then I'm going to add 1 to register 2 because this is my seed. So put in the 1, add 1 to register 2 and put it on register 2. Then I am going to add -3 to register 2. So what am I doing here is I already have a 1 in register 2, right? And I have the -3 added to represent -2. So what I'm doing is I'm getting ready to set up n minus 2 because it's f of n minus 1 plus f of n minus 2. So that represents my function. So here is where I would have the -3. Then after that, what I'm going to do is I want to look at how n minus 2 would be. So I would take the register 2, which has -3, add it with register 1, which has n. So I would have n minus 2. Can I just add -2 to register 2 and then add it with that? Sure. But we're going to do something with this because the reason why we have the -3 is I want to kind of really represent how the Fibonacci sequence actually start after the first two values. It is at the third position. And then we want to check for positive, right? Remember that that was one of the criteria is for overflow. So we want to check to see if it's greater than 0. So I'm going to go ahead and do a branch for the positive, and it's going to go to POS. And so for the next line after the branch, I'm going to clear register 4. And at this point, register 4 is 0. And then what I want to do is, because now I'm doing the overflow control here, right? So when you look, this is what we're doing. That we need to get 3 to I, and then we are going to try to make it greater than 0. Okay, we're checking. Okay. So here is where I'm going to add 1 to register 4 because I want to represent that F is 1 if it is negative. Okay. And it tells us that here. You see. Okay. F is 1 if it's negative. So we just branched to check for that. And then we worked on this right now. F is 1. All right. So coming back here, we already at this line. And then what I wanted to do after this point is earlier I have R2, right? R2 is going to represent your F of small n. So I need to store it to F of small n. We're going to store the result from register 2 to F of small n. And then what I have next is I have it branched to skip. And skip is going to be halt. Any question? So as we branch for the positive, this is now we're going to work on that part, right? Your A, your B, and so on. So let's look at this. Okay, so we did this part. F is 1. Now we got to work on this part. Okay. So for the positive, I'm going to go ahead and clear out register 2. We previously use it, so it's best that we clear it right now. Okay. And right before that, you see that I store already. So I clear register 2. Then I'm going to add 1 to register 2 and start on register 2 because my R2 is 1, which is represent A is 1. Then I clear R3. And my register 3 is going to be B. So I'm going to add 1 to 3 because remember that's our starting point, my seeds, right? So R3 is 1 and B is 1. And then I have register 5 is going to be my N, which is register 1 earlier, as you recall, right? We load N to register 1. And what we want to do with that is we are going to take the N and we're going to subtract 2. So N minus 2 is going to be in register 5. So we want to represent your f of n minus 2 and f of n minus 1, right? Okay. Then what we're going to do next is we are going to have a fab. Okay. Where this is going to be the function or the area where it's going to generate the f value. B plus A, and A is equal to B and B is equal to F. So what section is this, you ask, right? This is going to be this section. Okay. So for this, I have a label called FAB. I'm going to use register 4, which originally represent my F from earlier, right? Register 4 was my F. It's going to store the result of register 2 plus register 3. And if you look back into your code, your A is register 2 and your B is register 3. So it's A plus B. This is where it's very important that you track your register, what that represents in values. So I know that my A and B is 2 and 3. So add those together. I have A plus B, and I'm going to put it on register 4. And now I'm going to do the reassignment. As we generate the F value in the sequence, we're going to increment it to the right. So the B becomes the A and the F becomes the B. So we are going to do a copy. We're going to take my B, which is registered 3, and then add it with 0, and then put it back on register 2, which is my A. So here is where A is equal to B. And as we generate the Fibonacci number, we move the A becomes the B and the B becomes the F. So this is where you would take the register 4, which is your F, and you add it with 0 to do a copy for the B. B is F here. And I would subtract 1 for the decrement. This is part of the loop process. So as it still is positive, because, you know, as you loop, you count. This one we count down, right? We increment down. So what's going to do, we decrement down. So what we're going to do is, as long as it's positive, it's going to come back here and redo this part. It's going to keep looping until it gets to 0, and it's going to exit. So once we have the branching to fab, it's going to come back here, right? And then as long as it checks for positive, if it gets to 0, we exit. We learned that. Then on the next line, I have the f of n. We're going to store it from register 4, which is our f, right? And we're going to put it on f of n. We're going to store the result to the label f of n. which is filled with an address. And then I would clear register 2 again. And I would add A to register 2, which is, I mean, sorry, 1 to register 2, which represent my A. A is 1. And then we clear register 3. And we're going to add 1 to it as well. B is 1. Okay, so if you look back at the document, right? We talked about the loop and the shift as we generate the sequence. Okay. Then after that, we're going to clear register 5 after we have A and B as 1. After we add the 1. Now we want to initialize our index, which is I at 2. So my R5 is going to represent I. Okay. And so therefore I'm going to add 2 because at index 2, that's going to be my initial C. Okay. So coming back here, right? We have to really implement this. N starts at 2. And then it's going to loop after the second position in the sequence. So more for my fab 2, what I have is I implement the function again. So it's going to be F is going to be B plus A. So my A and B are added here. And I wanted to put it on register 4, which is represent F. So in this section, you would refer to the yellow listing that you see on the document. That's what we're working with to solve the problem. Is we have to piece it line by line and be able to get it as a Fibonacci sequence. So for now, what I'm going to do is I'm going to do the branch negative, right? This part. And so if it's less than 0, right, we're going to represent the big N as I. We already know that register 5 is I. So that would also be big N. And so, but we got to work on these. So for branch negative, we check for less than 0. We are going to copy the register because we reassign A plus B. Or I'm sorry, A as B. So here's my B. And I copy that to A. So A is equal to B. And then my F is at register 4. So I add it with 0 to copy it to B, which is at register 3. And you don't have to load the label. You just think about what that register means when you're solving the problem, right? And then I know that my index is represented with register 5 from above. So I would take that and I'm going to increment it by 1 because as you generate the next number in the sequence, it's I plus 1 as I. So it is I is equal to I plus 1. So here is my I plus the 1 equal to I. And as long as it's branching positive, I'm going to come back to Fab 1 and then this is a loop. So it's going to keep going. Right? If it branched for negative, Fab 2, when it branched for negative, it's going to go to the next section. So for the negative here, this is where we define the negative. Okay, any question regarding this part? So this part implements this area right here, right? The I plus 1, B is F, A is B, and we check for negative. Then for negative, since we branch it for negative and EG, we need to define it now. So we're going to clear register 6. And I want to make N is equal to I. You just saw that from the listing. So I know that my index is in register 5. That's my counter. And so I would need to copy it and put it on register 6. And so here, register 6 represent the big N, capital N. And so once I have that, I store that out to the label, the actual label, capital N. And I know that earlier I copied the F to R3 or register 3 because B is reassigned as F. Then I can then store register 3 out to F of N, the big N. And we had used the skip, so skip is going to be halt, right? That was part of the listing as well. It says that if it's like this, then stop the program. And then our data section, your small n, we fill it at hex 3100. Your f of small n is subsequent to it. And you want it to keep it together so when you simulate, it's not confusing. Right? And then for your big N, it's going to be 3102, hex 3102, and F of big N is going to be at hex 3103. And then to finish it, you would do a dot N at the end of the program. So in this code, what you see is you would see that we implemented the requirement, right, for Fibonacci. And this is using iteration. When you write it in C++, however you write it, or in another language, what you see is this is a way that we do reassignment and we implemented loop. There are other ways that you can also write with a nested if inside a loop. So there are a few ways that you can address the Fibonacci sequence in how you implement your algorithm. And this one way is to implement the loop. And then we put in the criteria for the reassignment of the value as we generate the F in the sequence. Any question? Okay, so once you have, yeah.
So just about the loops. There's only, I forgot. Just about the loops, like how many loops there are.
So this is your loop to generate your F of N, right?
Yeah.
There are Fab 2, and then there's another loop here.
Okay.
Because if you look, as long as it's branching positive, it's going to come back. So it's a loop, right? So
Uh-huh.
if I'm subtracting one, if you think about a loop, you can either increment or you can decrement. If you start at 0, you would increase. If you start at a value like n, you would decrease. You would subtract. Okay.
Okay.
So here is where if it keeps subtracting 1, as long as it's positive, it's going to come back here and do this again. When it subtracts it and it gets to 0, it's going to exit and it's going to go here and store the f of n. So to generate f of n for the first round, it's this. Now, the reason why we did it twice is because we have to make sure that we do overflow control. So when we generate the second part is where it's using the index with the for loop, and when it's less than 0, then it's gonna branch for negative, where it's gonna go here. Okay. Remember that they ask us to do this. So in the case where if we simply do a function to compute Fibonacci, it would just be a loop like this. Just this, fab1. But because we need to do the control for the overflow, it needs to check for the negative. So we have to implement this. That will be fab2. Okay.
Understand now. Thank you.
That's why I don't like.
I'm sorry.
Sorry, there's someone sitting next to me.
Okay. So in the case where we branch for the negative, that's to address if f of n is less than 0, right? And then we would put this in. That's the condition for the overflow. And we would implement this. So normally you would see branch, right? When it branched back to the label, that's a loop. Okay. But when you branch to like for comparison, you don't see the increment or the decrement in it. Okay. Because we don't need to count up or count down for the if else condition when we branch for it. So to check to see if it's positive or negative, if it's negative, it's going to go here, right? So you see that within the loop itself. So this is a loop with the nested if. All right. So after this, I will show you what that looks like in C++. So it's a lot, probably for most of you, it's a lot more friendly when you look at C++, and when you look at the code, it's going to make more sense too. But when you pseudocode it out based on the listing that's required, this is what it looks like. When you write it in LC-3. So once you have that, let me open up my simulator. So you need to assemble it, right, in the editor. So here's my ASM. Make sure you assemble. And then if you guys are using the online simulator, right, you just copy and paste your code on it. And then assemble it using the online one. So once you have the object file, you open up your simulator. And you are going to open up your program, assemble program, that is. Now, I'm going to run it without setting values so you can see. Okay. If we run it without setting value, we can jump to, what was it, 3101? If you don't set value, you're not gonna have anything there. You see that? This program is intended for you to set value to your n. Okay, so if I need to find the 10th number or the 6th number or the 9th number in Fibonacci, what would that be? And so on the normal value, so in the case where it's overflow, that means that it's going to be for a very large value. So to control the overflow, we would be able to utilize the subsequent address, right? That's what we put this in for the big N to be able to see. Okay? Because remember that there are so many limited bits in a word that we can store our value. And n can be a large number or small. So let's reload the program. And then before you run it, okay, you are going to set value. Where am I setting? I can set my n. Okay, at 3100. Let's say that I want to find the 8th value in Fibonacci. Okay. And then if you want to check to see if you set it, jump to 3100, right? It shows my 8 there. And then I can run. Once you set the value for n, what you can do is you can run the program, then you're going to jump to hex 3100. And it tells me here that for the 8th value, it is hex 15. And you can compute that manually to check, right? But this is what the computer generates. So make sure that we set the value for n. And then we can look at the output in the subsequent address after we run the program. You can test it with other value to see if your overflow works. And so in this program, what you see is we are implementing the algorithm, and instead of using variable and labels for everything, right, we just only use it for the ones that were required, which is your n, your big N, your f of small n, and f of big N. That's where you're going to see the input and the output. That's the whole point. So, and we use register for everything else. And also in this program, we are able to implement branching to check for comparison when it's negative. We're also implementing looping, right? for Fibonacci computation. Any question? Okay, so fairly easy, really short. I didn't want you to answer any additional questions. What I want you to take away from this is to understand how we implemented, right, the criteria that's given to us in the problem and how we compute Fibonacci using iterative approach. Okay. Now, is that going to be fast? Not necessarily. There are other ways to implement Fibonacci algorithm. However, this is the simplest way to kind of show you how we can implement loops, and we would be able to compute and control overflow based on what's asked. Okay, so when you're done with the program, I need for you to give me your screenshot of your code and your output. So you need to set a value and then run the program and check to see if it's accurate. Okay, so I need to see that. Now go through the code again and understanding what it's doing at what step and how that's based on this, right? And if you're not sure, this is how we implement function for Fibonacci in loops mostly. Okay, so let me go find my C++ program so I can show you. I did a lab in my CIS-11 with Fibonacci, so it's very similar to some of the ones I've done. I think I did recursive function, looping, for the Fibonacci lab. So 1 second. Some of my stuff here. Let me see. Okay. So I put this is called the optimized version of Fibonacci. Let me reshare my screen so you can see. I have it on my repo, so. So in C++, it's like this, right? I have a function, and then I'm passing this variable. I have A initialized at 0, B is 1, F and I. And then I said if N is equal to 0, return A. Then I start my for loop. I is 2. And if I is less than or equal to N, increment I. F is equal to A plus B. A is equal to B. B is equal to F. The reason why we do this, as we generate it, right, we are shifting the number to the right. So RC from RC to the right side. So this is what you see. And then return B, right? In the main, and this is what I hard coded. So if we test for N is 9, right, it's gonna see out. And I call the function here, plug in my, pass my variable N, which is initialized for 9 and return 0. And that's how you write it in C++. which is what we implemented in LC-3 today. Okay. So this is an optimized method of Fibonacci where you do the variable reassignment with a loop. And to be full blown with this, I could have implemented the if else statement like what they state in the criteria, which is what we see in the LC-3 side. But the big picture is your main functions like this. And in LC-3 today, we didn't do function call. So that's to come in the next couple of weeks. So you would see that down the line where we do a JSR, the function call, and then within the function, we would implement the loop like this. Okay, do you have any question? All right. So, because I know most of you are familiar with C++, so this is an easier way to kind of show you what we did, right? But in LC-3, sometimes it looks a little bit different because it's LC-3 and it's low level steps or, you know, so you got to piece everything in smaller chunks and be able to handle it. Okay, but the hard code here is I initialize value for n and used to set the value for LC-3. Okay. So somewhat of a short lap today. I think from here on out, we're not going to do multiple exercises. I think because our exercises are going to get a little longer, right? And I told you last time that I would turn on the extra stuff. So let me see if I did that for you. Let me check the page real quick before I turn it on. Oh, I only have Kevin's one. Let me see if I put it on my GitHub, and if I have other solutions on there, I'll link it and add it to the page for you. So you can see how other people solve the month of the year exercise from last week. Okay, so with that, I'm gonna go ahead and stop recording.